Take a moment to read through the question prompt, try to visualize what's going on. Here we have multiple forces acting on an object. Forces are a vector quantity, and we want to find the net force vector. It doesn't matter that at this point of the class that we don't know what forces are. Forces are vectors, and we know how to add vectors. If we want to find the net force, the sum of the overall force, we can find that by summing up all of the individual force vectors to give us the net force vector. If we're trying to add vectors like this, what we'll do is add them by components. So what we want to do is to draw each one of these vectors separately, find its components, and then we'll be able to combine those to find the overall vector. So we'll start with the first force here. We'll draw a coordinate system, and we're looking for a vector with an angle of 325 degrees in standard form. Remember, standard form starts at the positive x-axis. This would be 0 degrees, and we measure counterclockwise from there. So this would be 90 degrees, this is 180, 270, and so if we want 325, that would be somewhat past 270. We'd have a vector that would look something like this, where again, this would be the 325 degrees. If I want to figure out what the x and y components of this vector are, I draw a vertical line through the tip, a horizontal line through the tail, and so those are my x and y components of vector 1. This would be f1x, f1y. I've made a triangle here for myself, but I don't have an angle in that triangle. I know that this is 325 outside, and together that's making a full circle, which is 360. And so that I can say my reference angle there is going to be the full circle minus the 325. And so I'll have an angle of 35 degrees there inside that triangle. I also know that the magnitude of this vector is 97.2. That's the magnitude. And that magnitude of the vector is always the hypotenuse of the triangle. So using this method, vertical line through the tip, horizontal line through the tail, means that the y component is opposite that angle, so I'll use sine there to find that side. The x component is adjacent to that angle, so I'll use cosine. Notice how I'm giving myself an extra decimal place. I'll round that off at the end, but I don't want to introduce rounding errors now. Also notice how this trigonometry is going to give us all positive values. I try to write my value with a little bit of space, and I'm just going to manually put a plus or minus there to make sure I have the direction correct. So I'm going to look in the x direction. My component in the x direction is to the right, so that it is in the positive x direction. Even though it's redundant, I'll go ahead and put a plus sign there, just that I'm in the habit of always putting a plus there. I can look at my y component. My y component is downwards, and downwards is the negative y direction. So I have my x and y components of f1. Now we'll do the same thing for f2. I'll start with a coordinate system. I'm still in standard form, so I'm going to start from the positive x-axis and go counterclockwise. For f2, I'm at 80 degrees. The x-axis is 0 degrees, and the y-axis is 90 degrees, so 80 degrees is going to be something along that direction. And then in this case, I know my magnitude here is 86.7, so that's going to be something. It's going to be something like the same size as the vector over here, although there's not really, at this point, since we have all the vectors separated and we're dealing with each one separately, the actual size doesn't matter, and at a certain point, you have to draw it big enough that you can do your annotations without, have the drawing be big enough that you can fit all of your annotations there. So in this case, I've got my 80 degrees here. I know that the magnitude of this vector is 86.7. And again, if I want to end up adding all these vectors together, I need to break this up into components so that I can add my vectors by component. So I'll draw a vertical line through the tip, a horizontal line through the tail. There's my x, and there's my y components. This would be the x component of force 2. This would be the y component of force 2. I've got a right triangle here. That's the whole point of that method, right? Breaking up into x and y components is that you get x and y components there. Again, notice the y component is opposite the angle. The x component is adjacent, so I'm going to use sine and cosine. And here, because of the way the angle is, my angle for my vector is already the angle in the triangle. So I'm going to go ahead and find those x and y components using sines and cosines, trigonometric functions. Again, I have my my components here, and these are going to default to be positive values. I'm going to look here, I'm going to see my x component is to the right, so that is a positive value there. I'm going to look at my y component is up, so that is a positive value there as well. And I'll repeat this step one more time to find f3. Here I have my vector 3. Technically it's 48.6, so it's about half the size of the other ones, but since I looked at each vector separately, it doesn't really matter what size I drew it. I need it to be this big so that I can draw my components. As we've done before, vertical line through the tip, horizontal line through the tail, and there are my x and y components. This would be the x component of f3, this would be the y component of f3. Again, I don't have the angle inside the triangle, but I can find that reference angle. And so I've got a 67-degree angle inside my triangle, and I can use my trigonometric functions to find the x and y components. I get my components, and now I want to check again. In my x direction, I'm moving to the right, so that is the positive direction. In the y direction, I'm moving downwards, and so that's going to be in the negative direction. So I've considered each one of my vectors. I found the x and y components. When I add those up, I'm going to add them by components. I like to lay everything out so I have all my vectors, and you'll see how we can just add down the list. So what I'm going to do is I'm going to write out each one of my vectors fully in component form. It's a good chance for me to double check what my values are. And then, like I said, we'll add by components. So now I have my vectors laid out in component form with the I hats and the j hats. I've accounted for each one of these. I know that if I add up all of these, F1 plus F2 plus F3 is going to give me my net force vector. And so I'm going to add up what those are equal to as well. I'm going to add up all these values. I can only combine the I hat values. I can only add up the j hat values. So I can just go down, write down the list and add up all my I hat values to find the x component of my net force. And then I can go write down the order as well and add those up to find the j hat or the y component of my net force. So now I have my net force vector. It's in component form, which is one way of expressing a vector, but we're being asked to give that vector as a magnitude and a direction. So we want the vector in its polar form. And so what we're going to do is we'll have to draw out this vector. We know that it goes 113.67 in the x direction. There it is in the positive x direction. We also know that it goes 15.11 in the negative y direction, so that's downwards. I've exaggerated the size a little bit, again, just to make it a little bit easier for us to do the drawing. If this vector has an x component and a y component, then the overall vector starts where the first one starts, it ends where the last one ends, and so our vector is going to look something like that, is going to be our f net. And so our x and y components come at a right angle, they make a right triangle, so we can find the magnitude of this vector as the hypotenuse of a right triangle. I can use Pythagorean theorem to find the value here. These are force vectors. They do have units of newtons, so my net force is also going to have units of newtons. I'm going to end up rounding sig figs. And so I would say that the magnitude of the net force ends up being 115 newtons is the magnitude. If I'm looking for the direction, I know two sides of this right triangle, so I can use I can find the angle inside this right triangle. I have an opposite side and an adjacent side, and so I can use tangent, inverse tangent, to find that angle. Notice how when I've drawn this triangle, I've dropped off all the negative signs. This is negative because it's downwards. I've accounted for that, but when I'm dealing with this as a triangle, when I'm using trigonometry, I'm just treating this as a right triangle, and I'm going to use all positive sides here. I get an angle of 7.6 degrees. That's this angle right here. That's our reference angle, the angle inside the triangle. I did the inverse tangent of the opposite over adjacent to find that. And so that's going to give me the angle inside the triangle. That's most of the way there. But remember that we want our angle in standard form. So we would measure from the positive x-axis. We would measure counterclockwise. So that would be the actual angle for our net vector. And we can see that this angle here plus our 7.6 degrees is going to give us a full circle of 360. And so we can say that the actual angle that we're looking for here is going to be 352.4 degrees. And so if we put all that together, we found the net force vector. Has a magnitude of 115 newtons, and it has an angle of 352.4 degrees.